Hello, welcome to the lecture for MRI, the Basics, Chapter 12, which is entitled very general signal processing, but it's really going to talk about signal processing as it applies to a few concepts with MRI image formation. So our distraction for today are these fun pictures from this a nice blog called Inside Insides. It's been around for a while and does somebody who takes MRIs of a lot of different things, mostly various fruit. And so this is a fruit that is hard to recognize. I'm not going to reveal what it is in the lecture recording here. We'll talk about this in class, have some fun. And there's a number of other examples. This is really quite beautiful picture of an onion here, and then a 3D rendering of this MRI. Okay, so in general, signal processing is referring to the analog and or digital manipulation of signals. And so we're going to look at a couple things related to signal processing. First off, when does our data acquisition occur? So when are we actually getting the signals in our pulse sequence? And then one sort of manipulation that we're making of the data acquisition is going to figuring out this technique called 2D multi-slice imaging. And then finally, really digging a little more into some hardcore signal processing and talk about the concept of sampling and aliasing. So I want to start off by going through an example of, now we've covered frequency and phase encoding. How does this play into our data acquisition and sampling? So you can see in this drawing, we've drawn the data acquisition window right here during, this is our frequency encoding gradient here. We have data acquisition occurring during this frequency encoding gradient. Beforehand, there's our phase encoding gradient here. And these dashed lines indicating that we do this stepwise increment of the phase encoding gradient to fully be able to encode our image. And then I'm going to add another annotation here, this important parameter we're now very familiar with of the repetition time, or TR. And so what we're going to do in this example that's a 2D gradient echo is we're going to be stepping through our phase encoding gradient amplitudes. I'm going to be reading out the data during the frequency encoding gradient, and then the data from this interval is going to be put in our k-space data matrix. So we're starting to take samples of our data. And in the phase encoding space, we're going to repeat this for different phase encoding gradient amplitude, which are going to fill in different parts of our data encoding matrix. So our lower gradient encoding amplitude over here might have a time in which we're doing no phase encoding gradient, in which case we fill in our central line of k-space, and eventually we'll also have to do our negative phase encoding gradient, and so get down and fill in our final line here of k-space. Okay, so we have two dimensions here of the data sampling. The up-down in this picture is our phase encode sampling. The concept of sampling becomes important and when we talk about aliasing and a potential artifact. And then in the left to right here, to mention this is our frequency encoding sampling. And you should note that one thing we're going to talk about in this lecture is there's the concept of the sampling time. Kind of zoom in to one of these frequency encoding gradients. During the data acquisition, and I'll draw it idealized here. Is that we have some total data acquisition time, sampling time at the bottom, TS. You see corresponding to this sampling time here. This is the total length that we're acquiring signal, and we're also digitizing this signal at some interval. Some time interval, so some sampling time, delta TS. So for example, a point here in our data acquisition might correspond to this column, the data encoding matrix, or a point early in the frequency encoding gradient or data acquisition would correspond to maybe some column like this in our data encoding matrix. Okay, so we're taking signal over this data acquisition window. We're actually going to have to digitize that signal at this specific sampling interval, delta TS. And then we're going to put this signal into our k-space data matrix. And the way we're going to fill in this full 2D matrix that we need to is we're going to be stepping through our different phase encode sampling points. And we're going to build up why we have to do, a certain number of samples here, or what some of the requirements of this k-space data sampling matrix are over the next few chapters. So we can also look at this case for the 2D spin echo data acquisition. And we should note here I'm going to note when the data acquisition would be. And the data acquisition here corresponds to the time of our GX, our frequency encoding gradient. And again, we're going to be stepping through our phase encodes to fill up our data matrix. We have the similar sampling during the data acquisition. So this is indicating here that in this case we're starting off with a large negative phase encoding gradient. We're starting off by filling in bottom of our data encoding matrix. And we have some intermediate negative gradient, and we would continue this process by trying to fill in this full 2D data encoding matrix. We should note for all the drawings here that in the spin echo pulse sequence, the data acquisition and the frequency encoding gradient are always centered around the spin echo time. So this is shown in this drawing. If we draw a line down here from the spin echo time, that it's going to go right down the middle of our frequency encoding gradient and our data acquisition. So this is the procedure for acquiring a data in a single 2D slice where we do these multiple repetitions with different phase encoding gradient amplitudes. And that gives us an image of a single slice. And now, almost always, we're actually going to be doing some sort of 2D multi-slice imaging when we're doing 2D imaging. So we're going to want to get an image for one slice and an image for a next slice and so on. Like the picture up here is showing of an example of 4 slices in a multi-slice imaging that we might want to acquire. So the first thing I want to look at is a little refresher from the Chapter 10 slice selection. Is how do we use our RF pulse to excite these multiple locations? To assess this, we want to remember that we have, with our magnetic field gradient on, let's call this some amplitude GZ0, but then we have this relationship that the frequency is going to be gamma bar times the gradient amplitude times the spatial position, or equivalently the spatial position is the frequency divided by gamma bar GZ0. And so our nominal RF pulse here is going to excite a slice. If we add our frequency axis and our flip angle here, our RF pulse, distinct shape, recall will excite just a region in frequency, which maps over here to a single slice. So this is the same picture that we used in Chapter 10. So over here in this picture, you might initially excite signal from one of these slices. And if we recall, the way we want to shift our slice is to actually keep the same envelope, but add in some frequency offset of our RF pulse. So here we're multiplying the pulse by e to the I 2 pi, let's call it f1 of time. This multiplication, let's say b1 of t is equal to that. So in the Fourier transform domain, this is going to lead to our flip angle, the function of frequency. Our flip angle profile as a function of frequency is going to be shifted by some value f1. And this, if you recall, has the effect of shifting the frequency of the RF pulse, is the effect of shifting our slice. So we could do this to excite an adjacent slice, and so on, right? We could multiply by sort of different offset frequency f2, which would lead to a shift of the slice profile to some different frequency location. Let's make it over here, so we can choose what f2 is, and here we can shift our slice in the opposite direction and cycle through. So we can take just our same pulse sequence, our RF pulse, except add in these frequency modulations to the RF pulse. And this will enable us to excite our multiple slices. Okay, so now that we've got the shifting of our slices by frequency modulating the slice selection RF pulses, now I want to look at how we do the timing of a 2D multi-slice imaging. And the way I'm going to draw this is you see got a little blue box around here, around our main it's a gradient echo pulse sequence. And I'm going to draw a little box representing that entire unit of the pulse sequence and annotate it with a number here, where this is slice 1. And recall that we have to do multiple TRs to resolve our image. So this is going to be TR number 1 as well. And so the way we do 2D multi-slice imaging is, what do we do next here? And the typical way to do it is in what's called an interleaved fashion, where right after doing this excitation and acquisition for slice 1, we're going to move on to doing the excitation and acquisition for slice 2. But for TR1, and then we're going to move on to slice 3, but still doing the first TR. So for example, we could represent this as the first TR means that we're doing this red phase encoding. And then when we've completed the same phase encoding for all slices, then we move back to acquiring data for slice 1. But now we're going to do TR number 2. So that might be some different phase encoding gradient here. And we'll move to slice 2, slice 3 for the same TR number, or the same phase encoding step that we need, and so on like this. So we're going to repeat our slice block. Next, for example, we would do a different phase encoding gradient, TR number 3 for each slice, and so on. So again, this is what is referred to as interleaving, where we're interleaving the acquisitions for our different slices to get our multi-slice imaging. Let me just annotate here the colors. This is going to be TR number 2 and TR number 3, for example, are going to be our different phase encoding steps. Okay. So let's just expand that picture so it's really clear what's going on here. And specifically, let's just look at our basic pulse sequence block here. Same as on the last slide. Okay, we're going to go between slice 1, 2, 3, 1, 2, 3, 1, 2, 3. And then what I want to highlight is just pulling out of that small drawing, again, what the G, Y, or our PE, our phase encoding gradient will be. And it said in the first TR, it might be this. High amplitude positive gradient, which is going to correspond to filling in one line here of K-space. Right, so we're going to go do this line, do this line, do this line for our separate slices. We might move on to our smaller orange phase encoding gradient. We're going to come in here and fill in our next lines in K-space, and so on. Maybe now we're filling in a line down here. And then recall what's going on in the RF here. Is we're going to have different RF frequencies, say frequency 1, frequency 2, frequency 3, that are going to correspond to shifting our slice to these different locations. And that's the difference between these blocks 1, 2, 3 of our pulse sequence at the top. Okay, so we took what was just acquiring data for a single 2D slice, and then we're going to interleave. So we'll acquire part of the data for slice 1, part of the data for slice 2, and so on. And then after we're done with that, move on back to slice 1, acquire next part of the data, slice 2, that next part of the data, and so on. So this turns out to have some important effects on image contrast. So here, I want to highlight what this is going to look like. And let's specifically pull out the RF. And then what I want to do is plot the Z magnetization for each of our separate slices. So the Z magnetization in slice 1, we'll call MZ1. The Z magnetization in slice 2, call MZ2. The Z magnetization in slice 3, we'll call it MZ3. And what's going to happen is because our RF pulses are only exciting one slice at a time, then they're only affecting the Z magnetization in the individual slice. And so again, recall, I'll use the same notation as the previous slide where I said I had frequency 1, frequency 2, frequency 3 of the RF pulse here. We're going to say this pulse is applied at frequency 3, or I'm sorry, we could start off with 3, but let's do 1. That's what we did before. Then the next RF pulse is at frequency 2. Next RF pulse is at frequency 3. And so on. Let's add all these in. So we can then work on that, adding our, and we'll start off, we'll assume we're in the steady state here, but let's plot our Z magnetization for slice 1, Z magnetization for slice 2, or Z magnetization for slice 3. Okay, and we're going to use our saturation pulse sequence, meaning that all these pulses here are 90-degree pulses. We could apply similar analysis to whether we're doing other flip angles or even particularly. Okay. So let's start off with the first RF pulse. This 90-degree pulse is going to result in 0 Z magnetization, so saturation of the Z magnetization for slice 1. And then we're going to begin T1 recovery. We're going to get to this next RF pulse for slice 2. And since it's a different spatial location, this RF pulse does not affect the Z magnetization for slice 1. So it continues to recover. We get to the pulse for slice 3. Once again, the RF pulse for slice 3 only affects the magnetization in slice 3, does not affect the Z magnetization in slice 1. So we continue T1 recovery until we get to the next RF pulse for slice 1. Now at this point, this RF pulse does affect the Z magnetization for slice 1. We get saturation, so we end up with 0 Z magnetization, and we repeat as we did before for our image contrast. So T1 recovery, not affected by the pulse on slice 2, not affected by the pulse on slice 3, only affected once we get to the slice selection pulse applied to slice 1, saturation, and so on. And then similar things are going to happen for the magnetization of slice 2. So after this first 90-degree pulse on slice 2, we're going to have 0 Z magnetization. It's not affected by the pulse for slice 3. It's not affected by the pulse for slice 1. Only affected by the pulse for slice 2. 90-degree flip angle, eliminating the Z magnetization, saturating that, and continues on here. So we need the next pulse that affects slice 2. And then we'll have the same pattern before this as well. And it becomes sort of the same pattern again for slice 3, where it's saturated by the 90-degree pulse on slice 3. It experiences T1 recovery till the next 90-degree pulse that applies to slice 3, saturated, and then T1 recovery. Okay, and we can fill out the beginning. We can fill out the beginning here of the Z magnetization for slice 3 as well. So this has now important implications on the contrast, right? And the way we're going to characterize that is we're going to define the TR as the time between when we apply 90-degree pulses on the same slice. So it's the same for each of these slices. And then we're still going to get this signal relationship where the signal is proportional to, in this case, m0 1 minus e to the minus tr over t1, where tr is the repetition time between the same slice. Okay, switching gears here, I want to get to the topic of digital sampling. And this is coming back to what we talked about at the beginning of this lecture, how we're going to be acquiring our data, we're going to be storing it in this data matrix, and we're going to be taking what is originally an analog or a continuous valued signal and converting this into a digital or digitized signal, which is the illustration on this slide. So briefly, analog signals are things that are continuous valued in amplitude and time, and so all of our electromagnetic waves and signals in the real world are analog, right? They exist sort of at every point in time or in every point in space, And the purpose of a digital or digitized signal is so we can store this information. Right? We need a representation, and in computers we can only represent that by a finite number of bits or samples. So we go through this process of what we call an ADC, an analog to digital converter. It's going to take an analog signal like the one shown at the top and convert it into a set of discrete or digitized values. And so there is some theory, sampling theory associated with this process of going from an analog signal, which is the top line here, to a digitized or digital signal. And I have to put an abbreviation in the middle of the process by which this occurs is the analog to digital converter, often abbreviated ADC. And there's really one very important principle here, and we're going to look at this in the Fourier transform domain because this is going to affect how we reconstruct the signals in our images. And that's what is being shown here, is that we have a signal in time. We take a Fourier transform, we get a signal in frequency, and in this case it's a sinc function, and so its Fourier transform is a rect function. And what's being illustrated here by this omega m is that this signal has a bandwidth, or often abbreviated BW, that is 2 times this omega m value. So we have, you can think of this generally as we have some limited bandwidth in our signal. In the case of frequency encoding, it turns out this can be directly proportional to the fact that we have our object, our subject, is finite in extent. And so what the sampling theory tells us is that if we take samples of our time series data, and the time between those samples is this value, delta TS, or sometimes referred to as the sampling rate, that what will happen in the Fourier transform domain is that we get repeated copies of our original Fourier transform. We get repeated at integer intervals of n over the sample spacing. Okay, so that's what's being indicated by this 1 over delta TS here. So I know this would be 2 over delta TS. This would be minus 1 over delta TS, and so on. This is really the key relationship in sampling theory that we're going to have to pay attention to, because the problem is going to come, and maybe you can start to see this, is, well, what if the sampling rate that we use in our time domain is not fast enough, and that then when we sample and we get these repeated copies of our Fourier transform, that if these overlap from each other, that's where we're going to have problems. Now, just to illustrate that we can also think of this in other domains, and the other domain we're often going to think of is going to be K-space. So let's say we're in Kx, and if we do a Fourier transform of that, say that goes into X, or the spatial domain. And here, this value here, I often denote that as the could be like the width of our object in the X dimension. But in K-space, actually, we're inherently digitized, so we have some digital sampling with some interval, say delta Kx. That means that the Fourier transform is repeated copies of our original object here at intervals of integer intervals over delta Kx. And I won't go through the derivation of why you get these repeated copies. You can derive it through the sampling function, which is a set of delta functions, and use Fourier theory to derive that. And the book actually covers some of this theory in there as well if you're interested. Okay, so here I was just changing basically the notation, moving from frequency and time to K-space and space. But for the rest of this time, we're going to stay in time and frequency. And when we get to chapter 16, we'll convert everything into K-space. Okay, so now we're going to go through the process of when we actually look at the results from, say, a Fourier transform, and what we're using is the discrete or the fast Fourier transform, is we don't see these repeated copies. We just see actually one copy. And let me walk through why that happens. Okay, so say we start off with some signal in time that has some profile and frequency, and we'll relate this continuous valued signal in time with the now continuous Fourier transform, and we get a profile like this. Now when we digitize this signal, some sampling interval, do my best here to kind of draw this, and we can label we have some time sampling interval here. Is that, well, what I just said is that we're going to get replicas of our original Fourier transform at these integer multiples of 1 over a delta TS. And that's if we look at things from the perspective of the continuous Fourier transform. Okay. But what actually the discrete Fourier transform, and we often call this the FFT because that's the algorithm that we used, but the discrete Fourier transform, all it does, it only gives us this central region of frequency. It's only that the frequency that's defined depends on the sampling interval. So the width of the region that's defined in the discrete Fourier transform is, I can see it from this, is 1 over this delta TS interval. So if we feed in a set of digitized samples like so into, get the idea here. If we feed these into the discrete Fourier transform, all we see is then what's sometimes referred to as the baseband signal, or this central region of what we would get with the continuous Fourier transform. Okay, just to illustrate again, why don't, when we're going to go ahead and do Fourier transforms on sampled signals, well, why don't we see a bunch of these repeated copies? And that's because of how the discrete Fourier transform is defined. So this signal in the middle row has this inherent repeating structure. So all you need to do is look at one copy of that to understand the whole signal. And that's the theory behind the discrete Fourier transform. Now, we have to choose our sampling rate carefully. And let's consider an example of a sinusoid here. And try and be a little bit precise here. And let's define a couple of parameters here on this sinusoid. First of all, this time here is going to be 1 over the frequency of this sinusoid. And then let's look at the Fourier transform of this continuously valued function, where this is a cosine, which the Fourier transform of a cosine is 2 delta functions. Positive f1 minus f1. Let's write that up here. Cosine 2 pi f1 of p. If we take the Fourier transform of that, we get delta 1 over 2, delta f minus f1 plus delta f plus f1. And that corresponds to these 2 delta functions, shown like so. Okay. Now, first, let's choose one sampling rate, and we're going to try and choose a rate that is sufficient to capture this waveform. So, let's say we sample at these red locations here. And you can see we've divided this 1 over f1 interval into 4. So in this case, our delta TS is 4 over f1. Oh, not quite. Again, 1 over 4 f1. So if we take the Fourier transform of this, we're going to get we have the original Fourier transform, and then we're going to have repetitions of this around, and they have to be a little off scale here since this is f1 minus f1, and have it repeated copies around 4f1 minus 4f1. So that means we're going to have a delta function here and somewhere at 3f1 and here at minus 3f1. And then recall that what our when we do the discrete Fourier transform, the only part of this signal that we look at is going to be something with a width of 4 F1 here. So cutting off the edges of this, you'll see, okay, we're actually going to be able to faithfully recover our original signal when we choose this sampling interval. However, we can start to make some poor choices of the sampling interval. Let's say we chose a coarser sampling interval, much coarser sampling interval. Like so, where now our sampling interval is 3/4 F1. So what's going to happen in this case? So we're going to get our original copy of our Fourier transform, but then we're going to have replicas originating from centered around, and it's a little tricky to draw, but 4/3 F1 minus 4/3 F1. Okay, so we're going to take these two delta functions, and they're actually going to start to overlap. So from here, we move down to F1/3, and we're going to get a delta function. We're going to get one over here at minus 7/3 F1. Same thing on the other side here. F1/3, etc. And then when we do this in the discrete Fourier transform, actually all that we'll see is going to be the center region with a width of 4/3 F1. So what does this mean? Well, we can actually look at this in the time sampling here. That means if you look at these orange samples and we try to think, well, what sinusoidal curve could be made from these orange samples here? Well, sure, maybe it could be the original curve, but what it could also just as well be this purple curve. And it turns out that this purple curve here is going to have a frequency that we can see from the Fourier transform that is going to be F1/3. And I know that because of how where these replicas showed up in this sampling theory interpretation of the Fourier transform, again, where we took the original Fourier transform on top. We started with that, but we added these replicas. In this case, these replicas were not far enough apart, meaning our sampling interval was too coarse in time, and thus we get what is called an aliased signal in this case. So this introduces the concept of aliasing. Okay, so let's kind of refresh that, and I'll do this with a different sampling rate here, just to illustrate again what's going to be going on with aliasing. So let's say got our same cosine, nice example here. We have this frequency of f1 in this cosine. And here I'm going to even make a worse choice of the sampling interval. Let's say, well, what if I chose delta Ts to be equal to 1 over f1. And, well, this looks kind of funny when we see it, but we're going to get a sample here, sample here, sample here. So we're basically only hitting the peaks of this cosine function. So what are we going to see if we look at the continuous Fourier transform interpretation? We'll get a replica of our original spectrum, but then we'll get these copies centered around f1, so we'll get one copy from this repetition. And here I'm going to add some more colors. In fact, get another copy from the repetition on the other side of the Fourier transform. And so now if we look at the discrete Fourier transform, where we're only going to be resolving this bandwidth of f1 based on the sampling rate that's been chosen, we're still going to have these same samples over here. And what we would see in this case in our discrete Fourier transform, or the result of the FFT here, is actually just going to be a single delta function at 0, which the Fourier transform corresponds to just a signal of amplitude 1. And we can actually add a little bit of units here. Note the height of this is 1. Actually, in all these other plots, so this is the height of these delta functions is actually 1/2, because the Fourier transform here is half of delta f minus f1, delta f plus f1. So when these orange and red copies at the middle overlap, they in fact add together to give us a delta function of amplitude 1 in this case, and corresponding to the best, and so the best knowledge we have of what this signal can be from this discrete samples, this is just a constant amplitude, and we can't, what actually the discrete Fourier transform says is we can't expect to resolve any frequencies outside of this range here. We can't, and this is like an unknown region because of the limitations of sampling and what we're going through here. So let's go through another example where maybe we have some now sort of fictitious object. And they often look kind of like a sinc function. And let's say it's some band limited object. So since we're in frequency, call this the bandwidth. And here I'm going to look at, let's draw an example. Before we saw the case of, I illustrated of, well, if our sampling rate was sufficient. What if it's not? And say, well, what if our sampling rate over here, we're going to choose our sampling rate such that it's bigger than this bandwidth. So what does that mean in this interpretation of the sampling theory? That means when we create the repetitions of this object, they're going to be centered around 1 over delta TS, which is going to be less than the bandwidth. Okay, so let's illustrate what that could look like and say, maybe it's samples that are too far apart. This is our delta TS. So what the sampling theory with these replicas tells us is we're going to get a copy of the Fourier transform of our object, but repeated. And since by this choice of the sample spacing, that means the distance, so here you can calculate this out. This location here is bandwidth over 2, but this, and add the other side, but the distance between this replica and this edge here, this, due to this sampling duration, this distance here is going to be less than bandwidth over 2. That means when we put our replica on here, it's going to overlap. Let's add a different color here for the other replica. We're going to get the same phenomenon on the other side. And then if we take the discrete Fourier transform result, which takes the same samples here, but then only resolves over this 1 over the sample spacing, which remember this is less than the bandwidth of our object, so I've been tried to be precise in the where I've drawn this limit here. We don't get any information on the outside here. What we're going to get is these signals, so these edges here that have wrapped around are going to add, so note that they're wrapping around. Okay, so we're getting this short end in the original object or spectrum here. When it wraps around on the right, the short end in red appears on the right side of the spectrum, and the high edge of this spectrum, when it wraps around on the left, appears at the left edge of the object. These things are going to add together. So in the center here, we're going to get our original object reproduced, but at the edge, we're going to have what was our original object plus this red portion here that wrapped around. So we can maybe color code that. This little red triangle that's corresponding to this little extra bit here. And then, we'd hope, normally we'd see that this left edge going to 0, but in fact this other high edge is going to be added on top of that. So this is corresponding to this area that gets what we call folded around or aliased. And this is the way that we come and see image aliasing in MRI. So these pieces here are aliasing, and what this interpretation tells us is it's a wrap around. Okay, it doesn't go out to the edges and fold back in. It goes out to the edges and wraps to the other side. And we'll see that in the imaging examples here as well. And what all this aliasing discussion leads to is something called the Nyquist Theorem. You may encounter this term. And this tells us, really gives us a guideline for how we need to do our sampling. So in time, it defines the maximum frequency range, or the bandwidth, that we can recover, and that this is the inverse of the sampling rate, delta Ts. So it's basically how far those repetitions of the Fourier transform are spaced apart. And it's basically just a redefinition of the terms, but in the case-based sampling, as we'll get to more in chapter 16, so the maximum space, which is the field of view, or FOV, that we can recover is the inverse of the case-based sampling rate, delta Kx. Okay, and this relates to this original sampling theorem, or theory, that says when we sample a continuous signal in the Fourier transform domain, it creates these replicas at the intervals defined, as you see on the right side of these equations. So this gives us a guideline for, well, how frequently do we need to sample our data in order to faithfully reconstruct an image. And, well, what happens if we don't? So here are a couple of examples. In the brain, on the left, we have an axial brain image with a sort of exaggeratedly narrow field of view. And we see that this region here should in fact be sitting out here, and this part of the skull should actually be sitting out here. In the other example here, this one's a little bit more subtle. If you look carefully at the corner here, we see that part of the nose, which was sticking out of the edge of the field of view on one side, aliased or folded around to the other side. Now, in some cases, we can actually do something about this. And so I'm going to start off to describe this by introducing the concept of low-pass filtering. And so, maybe we start with an object that has some wide bandwidth here. So it has some higher frequency oscillations. It's going to oscillate faster if it has higher frequencies. And what we're going to do, and what we can do with continuous valued signals like time signals, is that we can send this through, and I'm just going to abbreviate it as a low pass filter, and get some subsequent signal out. But really what the low pass filter is best thought of in the Fourier transform domain. This low pass filter is equivalent to multiplication of this original spectrum by some function like so. Put some axes on here, so that's basically 0 outside of some bandwidth, and it's 1 inside of the bandwidth in the case of an idealized filter. So perhaps best illustrated by what the result is of that, which is going to be, we're going to get a spectrum in which we only retain the low frequencies. This is hence the name low pass filtering, is we're only allowing the low frequencies to pass through this filter. And just kind of making up a drawing, but basically you could imagine what it will sort of look like is that, just trying to remove a little of those higher frequency oscillations, right? There's remove some of the higher frequencies in this object. This is just a sketch, not an exact drawing. Okay, and so then now we can come into this object and we can sample it. And we can choose this sampling interval to match the bandwidth of our low-pass filter. So this low-pass filter has only some range of frequency values that it allows through. And so we can match our sampling to the range of frequency values that we know we're going to get. So then when we do these replicas at intervals of the bandwidth of the low-pass filter, we have a guarantee that they won't overlap with the original object, or when we go to our discrete Fourier transform, where we just have these samples, then we're only going to get this central region that is the same bandwidth as our low-pass filter, and we're just going to see the central region of the spectrum. Again, the discrete Fourier transform is not defined outside of this region because it's just repetitions. And the other term for this is an anti-aliasing filter. Okay, let's just go through that same example, maybe a little bit. Different object here. I don't know, just making up a signal here. But we're going to do our low pass filter operation, or now we're going to call it an anti-aliasing filter because that's its purpose. And I'll use the abbreviation AAF, anti-aliasing filter. So we're sending this through our anti-aliasing filter. And so then we get some version of this where I just smoothed out some of those oscillations. And this object has a limited extent frequency space because of this anti-aliasing filter. So you can come in with our analog to digital converter now. our ADC. Represented by the red here. Just draw a few more of these out, but you get the idea, of course. And if we look at this in the continuous Fourier transform interpretation, these replicas, again, will not interfere with each other, since these are at these intervals of the anti-aliasing filter. And we look at our discrete Fourier transform performed by the FFT, and we just get what is the central region of our object, and we guarantee that there is no aliasing in this way. And as we'll discuss later on, turns out we can't always do the anti-aliasing filter. We can only do this when we have time series data, which turns out to be our frequency encode dimension. We cannot do this in our phase encoding dimension. But still a very, very powerful tool that we have, and I think a nice illustration of the sampling theory in action, as well as the concept of a brief introduction of the concept of filtering here. So let's drive home this point. No aliasing. Hooray. Never would be so excited about no aliasing or about anti-aliasing filters. So this wraps up this lecture on some of these signal processing techniques. And remember, as you're going back through this material, think about when does our data acquisition occur in our pulse sequence, and how is it filling up our data matrix. We covered a bit in how the 2D multi-slice imaging works. And then at the end, we looked at a little bit of the theory behind aliasing and how aliasing can occur. And then, of course, right at the very end there, what is anti-aliasing filtering. Great. Thank you very much for watching.